Alright, in this video we're going to be using derivative tests to find different characteristics of graphs, like their increasing and decreasing intervals and their relative max and relative min, so that we can eventually draw a sketch of a graph without using our calculators. So this is derivative tests to sketch functions. So if a function has a positive slope, and a positive slope of a function would be located where the derivative is greater than 0. So if the derivative is the instantaneous rate of change, then this is saying that the derivative at individual points, so specific x values, if that derivative is positive for a section, like multiple x values in a row have a positive slope, that means that the function is increasing. So if you want to draw like a little sketch over here off to the side, if we had a graph that looked like this, all these x values right here would have rates of change, instantaneous rates of change that are positive. We would have positive slopes for the tangent lines for all the points over here. And this part of the graph you would say is increasing, and then it hits this maximum point, and then it decreases, and then it hits this minimum point, and then it increases again. So that's all we're talking about, is that all these points right here would have a positive derivative. So we also know that if a function has a negative slope, so the derivative is less than 0, then the function is decreasing. So what we're going to do is we're going to take a function, and then as we work our way through the notes, we're going to find little bits about this function until at the end we can go ahead and sketch a picture of it. So the first thing that we are going to do with the function is we are going to find the increasing and decreasing intervals. And the function that we are going to work with is f of x equals x to the 4th minus 4x to the 3rd plus 2. So the first thing I want to do is I want to find the derivative, because I have to know where the derivative is positive and where the derivative is negative for me to know what the increasing and decreasing intervals are. So my derivative is 4x to the 3rd minus 12x squared. And if I want to know where the derivative is positive and where the derivative is negative, then I should solve for where the derivative equals 0, because 0 is the number that's in between positive and negative. So if I can see where it crosses over, where it crosses from positive to negative, then I would be able to know those numbers that are in between. So 4x to the 3rd minus 12x squared equals 0. I can factor out a GCF of 4 and x squared, and that would leave me with x minus 3. So we're going to go ahead and make a sign chart. On the sign chart we have the numbers where the derivative was 0. So we've got a derivative of 0 at 0, and a derivative of 0 at 3. So now I need to look at my derivative and see what numbers would make the derivative positive and what numbers would make the derivative negative. So first I'm going to look at the numbers that are to the left of 0 and see what's happening there. So at an x value of negative 1, if I plug negative 1 in right here, 4 times negative 1 squared is going to give me a positive answer. Negative 1 minus 3 is going to give me a negative answer. And if I multiply positive times negative, I get negative. A number that is between 0 and 3 that I could plug in would be like 2. So 4 times 2 squared is going to be a positive number. 2 minus 3 is going to be a negative number. And so this is negative right here. And then last, a number that's bigger than 3 would be like the number 4. And if I plug 4 in, 4 times 4 squared is positive. 4 minus 3 is also positive, and so this is a positive number right there. So we would say that the graph is decreasing right here. It has a horizontal tangent line at 0, and then it's decreasing here, and it has a horizontal tangent line at 3, and then it is increasing at that point. So decreasing, these are negative slopes, these are slopes of 0 at these 2 points, and then this is our positive slope right here. So I'm going to say that my increasing interval is from 3 to infinity, and my decreasing interval is from negative infinity to 0 and 0 to 3. Well, don't skip 0. That was me not thinking. Negative infinity to 3. Don't skip 0. Okay. So overall the graph is decreasing, overall the graph is increasing. Okay. The next thing that we want to take notes on is called the first derivative test. And this is the actual name of the test. And sometimes you'll read instructions that will say something like use the first derivative test. So you want to make sure that you understand what this test says and when to use it. So given C, and C is a critical number, and it has to be of a continuous function, we have some conclusions we can make. And if you recall, a critical number is in one of two cases. It could be where the derivative equals 0 or where the derivative is undefined. So we have actually already found the critical numbers for this problem above. The critical numbers would be 0 and 3. All right, so here's what it's saying. Given your critical number, if the derivative changes from positive to negative at the critical number, then f has a local max at that critical number. So if you think about this, if the graph is going up, so the derivative is positive, that means the graph is going up, and then it switches and it comes down again, that would mean that you have a maximum. And that kind of makes sense. That's what we've looked at before. If the derivative changes from negative to positive at the critical number, then f has a local minimum at C. So if the graph is going down and then switches to going up, that's where a minimum would be located, is that C value that made it switch. And then last, if the derivative doesn't change signs at C, then there is no local min or max at C. So if we consider the problem that we started working with, our two critical numbers are 0 and 3. And if you look at 0, it says the graph was decreasing and then it continued decreasing. So we're going to say x equals 0 is no local min or max. There might be a horizontal tangent line there with a slope of 0, but it's not a min or a max. If we look at the other critical values, that was where x equals 3, we can see that the graph was decreasing, it was going down, and then it started increasing and going up. And so that means that this must be a local minimum. Now, if you want to find the actual x and y coordinate of the local minimum so you can write that point down, you need to look back at the original function to be able to write those values. So x value for sure, and then if I look back at the original function and plug that in, I have to locate my calculator, then I've got 3 to the 4th minus 4 times 3 to the 3rd plus 2, and that's a y coordinate of negative 25. So that means that the local minimum happens at the point 3, negative 25. All right, next we're going to look at the concavity test. The concavity test says if the second derivative is greater than 0, then the function is concave up. So that means that if the second derivative is positive, that part of the function, whatever that interval is, you're going to see that the graph looks like an upward U at that at those points. If the second derivative is less than 0, or if it's negative, then the function is concave down. So this is going to feel somewhat similar because we're doing the same process. We're looking at the second derivative and we're looking at where it's positive and negative, which is just what we had just done with the first derivative. So it's going to feel very similar. Now there's a point that you probably have not heard of called the point of inflection. And the point of inflection is a point where the function changes concavity. So I'm going to draw two pictures of this so you can kind of see. So in this picture, I would say the point of inflection is about right here. I'm not going to say exactly where it is, but this part of the graph is concave down, and then it switches to concave up. So that would be the point of inflection here. On this one, this would be the point of inflection because this piece of the graph is concave down, and this, no, sorry, concave up. This is concave up, and this piece of the graph is concave down. So the point of inflection is where the function changes its concavity. So the next thing we're going to do is we're going to take that original function that we had and we're going to find the second derivative now. So the first derivative we had was 4x to the third minus 12x squared. So I'm going to go ahead and copy that. 4x to the third minus 12x squared. So now we're going to find the second derivative, and that would be 12x squared minus 24x. And we're going to do the same process. We're going to take that second derivative and set it equal to 0, because if we're looking where the second derivative is positive and where it's negative, 0 is in between those values. So if we can figure out where it equals 0, then we'll know what's happening on either side of those zeros. So I've got a GCF of 12x that I can take out, and then that leaves me with x minus 2. So x equals 0 and x equals 2. And I'm going to go ahead and make a sign chart again so I can check these values. So a number to the left of 0, would be x equals -1. And 12 times -1 is negative, and -1 minus 2 is also negative, and a negative times a negative is positive. So this would be concave up. A number between 0 and 2 would be like 1. So I've got 12 times 1 is positive, and 1 minus 2 is negative, and so that's negative. And then a number bigger than 2 would be like 3. 12 times 3 is positive. 3 minus 2 is also positive, and so that would be a positive answer right there. So if we look at this and we want to describe where the U-shapes that are going up are, where those upward shapes are, we're going to say that's from -infinity to 0 and from 2 to infinity. And then the graph is concave down from 0 to 2. Now, if we want to locate the points of inflection, the points of inflection are located where you switch from concave up to concave down, or where you switch from concave down to concave up. So we have 2 points of inflection. One is at an x-coordinate of 0. The other is at an x-coordinate of 2. So if we want to know what the y-coordinates are for those points, we do have to go back to the original function and plug 0 in and plug 2 in. So 0 to the 4th minus 4 times 0 to the 3rd plus 2. And then 2 to the 4th minus 4 times 2 to the 3rd plus 2. All right, now at this point we do have enough information to actually sketch a graph for this. Go ahead and put my little graph on my notes. Okay, so we had some points over here. We had the point of a local minimum that was 3, -25. And that's going to be hard to graph, so I'm going to go ahead and make my little boxes go by 2s. And yes, you should be graphing this as well. So the point 3, -25 would be about right there. And then we have our points of inflection, which are actual points you can graph. So I've got the point 0, 2, and 2, -14. And the graph says, if we look at the information that we found already, we are increasing from 3 to infinity, and we are decreasing from -infinity to 3. And so that kind of fits what we have. We're going to say that the graph is decreasing from over here all the way down through these points to 3, and then after 3 the graph is going to be increasing. And then if we look at the concavity, we're going to say that it is concave up, so we're going to see a U-shape going up until it hits 0, so this part must be a U-shape going up. And then concave down from 0 to 2, so it's going to look something like this. So if you can see, this little part is concave up, it's kind of like a U-shape going up. This little part is concave down, that's like a U-shape going down. And then it's concave up again from 2 to infinity. So there's the U-shape going up, and then it hits that minimum point and goes up again. Now I don't know what the x-intercept was, it might not have been 5. So this sketch may not be perfectly accurate, but if you graph it on your calculator, you're going to see that that is a reasonably accurate sketch. So we're going to go ahead and graph the original and see how accurate this is. And I am going to have to change my window. Ooh, look at that. It's pretty nice. I'm going to have to change my window to make sure that the y goes down to negative 25 at least so we can see the whole thing. There we go. Pretty accurate picture. Kind of cool, huh? Alright, we have just one more thing you're going to add to your notes, because if we have a first derivative test, it only makes sense for us to have a second derivative test as well. So here is the second derivative test. So if you look back at your notes, the first derivative test was a way for you to find a maximum and a minimum. So the second derivative test is also a way for you to find the local max and local min. So here is the second derivative test. If the second derivative is continuous near C, and C is an x value, then we have two things that we can look for. First, if the derivative, when it's evaluated at C, equals 0, so we're basically saying if it's a critical number, if it has a horizontal tangent line, and the second derivative at that point is greater than 0, so we're saying not only does it have a horizontal tangent line, but it is concave up, so picture this, concave up, it's this point right here and it has a horizontal tangent line, then there's a local min at C. If the first derivative evaluated at C is 0, so again we have a horizontal tangent line, and the second derivative evaluated at C is less than 0, so now it's concave down. So here's what our picture looks like. We're concave down. At the C value we have a horizontal tangent line. Then F has a local max at C. So this is another way you could look for your local max and local min. Two different ways of doing the exact same thing.